Welcome to Physics Concepts Podcast. I'm Amara, and today we're exploring one of the most fundamental principles in classical mechanics, Newton's second law. Whether you're designing spacecraft, analyzing collisions, or understanding everyday motion, this law is absolutely essential.
I'm Marcus, and what makes today's episode particularly interesting is that we're not just discussing the theory, we're examining how experimental methodology validates this principle. Newton's second law states that the net force acting on an object equals its mass multiplied by its acceleration, F equals ma. But how do we actually verify this relationship in the laboratory?
Excellent question. Let's start with the fundamentals. Newton's second law is a vector equation, meaning force and acceleration point in the same direction. The constant of proportionality is mass, which represents an object's resistance to acceleration, or inertia. When we apply a force to an object, the resulting acceleration is directly proportional to that force and inversely proportional to the object's mass.
So if we double the force while keeping mass constant, we double the acceleration. Conversely, if we double the mass while keeping force constant, we have the acceleration. This inverse relationship with mass is crucial for understanding dynamics. But here's where experimental design becomes critical. How do we isolate and measure these variables accurately?
That's where the Pascal dynamics system comes in. In a typical university experiment, students use a cart on a frictionless track with a force sensor and motion sensor. The experimental setup involves applying varying forces to the cart and measuring the resulting accelerations. Let me walk through the methodology. First, you establish a controlled environment, a level track with minimal friction.
Why is minimizing friction so important?
Because Newton's second law describes net force. If friction is present but unmeasured, it becomes a hidden variable that corrupts your data. By using a nearly frictionless surface, the applied force becomes the dominant net force. The force sensor directly measures the applied force in newtons, while the motion sensor tracks position and calculates acceleration from kinematic data.
Let's look at actual experimental data. Consider a cart with a mass of 0.360 kilograms. When researchers applied forces of 0.076 newtons, 0.109 newtons, 0.136 newtons, and 0.175 newtons, they observed corresponding accelerations of 0.136 meters per second squared, 0.266 meters per second squared, 0.339 meters per second squared, and 0.519 meters per second squared. What does this tell us?
If Newton's second law holds perfectly, we should calculate mass from each trial using m equals F over a. For trial 1, 0.076 newtons divided by 0.136 meters per second squared equals approximately 0.559 kilograms. But wait, that doesn't match our known mass of 0.360 kilograms. Why the discrepancy?
This is where experimental methodology becomes sophisticated. The force sensor measures only the applied force, but the system includes the sensor's own mass. Additionally, there's the hanging mass that provides the driving force through a pulley system. The actual accelerating mass is greater than just the cart alone.
Precisely. If we account for the force sensor's mass and the system's total inertia, the calculations align beautifully with Newton's second law. This demonstrates a critical principle. Experimental validation requires understanding your entire system. You cannot simply plug numbers into an equation. You must comprehend what each measurement represents physically.
Let's discuss the force-acceleration relationship more deeply. When we plot force versus acceleration, we should obtain a linear relationship passing through the origin. The slope of this line equals the total mass of the accelerating system. This graphical approach provides immediate visual confirmation of Newton's second law.
And if the relationship isn't perfectly linear, that's informative too. Deviations suggest systematic errors. Perhaps friction wasn't adequately minimized, or the force sensor wasn't properly calibrated. Good experimental design includes error analysis and uncertainty quantification. You should report not just your results, but also your confidence in those results.
What about more complex scenarios? Newton's second law applies to systems with multiple objects. Consider two masses connected by a rope over a pulley. You must apply F equals ma to the entire system first, then analyze individual components. The tension in the connecting rope becomes an internal force that you can calculate once you know the system's acceleration.
For example, if a 2-kilogram mass and a 4-kilogram mass are connected, and you apply a 12 Newton force to the system, the total mass is 6 kilograms. The acceleration is 12 newtons divided by 6 kilograms, which equals 2 meters per second squared. Now, to find the tension in the rope connecting them, you apply F equals ma to just the 2-kilogram mass. Tension equals 2 kilograms times 2 meters per second squared, which is 4 newtons.
This hierarchical approach, analyzing the whole system first, then individual components, is essential for solving complex dynamics problems. It prevents confusion and ensures consistency. The same principle applies to Atwood machines, where gravitational force drives the system, or inclined planes, where you must resolve forces into components.
University-level physics demands this systematic thinking. You're not just memorizing F equals ma, you're learning to construct free body diagrams, identify all forces, resolve vectors, and apply Newton's laws methodically. Experimental work reinforces this by showing that theory matches reality when properly executed.
What advice would you give students conducting these experiments?
First, understand your apparatus completely before collecting data. Second, perform preliminary trials to identify and minimize systematic errors. Third, collect multiple data points across a range of conditions. Don't rely on a single measurement. Fourth, analyze your data critically. Does it match theoretical predictions? If not, why? That investigation often teaches more than perfect agreement would.
And finally, document everything. Your methodology, your uncertainties, your assumptions. Science is reproducible. Someone else should be able to read your report and replicate your experiment. That's how knowledge advances.
Newton's second law is more than an equation. It's a framework for understanding motion. Whether you're analyzing planetary orbits, designing vehicles, or studying particle physics, this principle underlies the analysis. By combining theoretical understanding with rigorous experimental methodology, you develop the skills essential for advanced physics and engineering.
Thank you for joining us on Physics Concepts Podcast. We've explored Newton's second law, examined the force-acceleration relationship, and discussed experimental methodology for university physics students. Keep questioning, keep measuring, and keep discovering.
Until next time, this is Amara, reminding you that physics is everywhere. You just need to look carefully and measure precisely.